Welcome to NeurIPS. Welcome back to Montreal. If you've been here before, live here, or welcome if this is your first time to NeurIPS or to NeurIPS at Montreal. This morning we're going to have a great tutorial on adversarial robustness, theory and practice. And let me introduce our two speakers today, Alexander Madry and Zico Coulter. Alexander Madry is a professor at MIT at the CSAIL laboratory, and his work focuses on optimization and robustness, in particular in deep learning. Zico Coulter is a professor at Carnegie Mellon and also the chief scientist at the Bosch AI Center. And his work focuses as well on optimization and on, in particular, rigorous, explainable, and robust deep learning algorithms. Please welcome the two of them, and let's enjoy the tutorial. Thank you.
So, welcome everyone. I'm Alexander Madry, and together with Zico, we want to talk about adversarial robustness. So, adversarial robustness is something that we sort of knew what it is, but it still caught us somehow off guard. And because of that, well, we have to now struggle. Okay? And actually, we wanted to use this opportunity to not only talk about adversarial robustness, but also to sketch a bit broader picture of the field and the challenges that we face when we try to deploy machine learning in the real world. Okay? So let's get started. Okay, so I think it's safe to say that machine learning is a success story currently. If you work on machine learning, there is plenty of opportunities to feel proud about yourself over the last decade. So we made progress on some of the flagship challenges that just a few years before we did not think are within reach. Now they are. So that's all great. And in particular, this kind of bred a lot of excitement. Okay, so now you can't open the newspaper without reading about all the great things that ML or AI will bring to us. And in particular, all of the successes essentially inspired people to kind of apply or think of applying machine learning to anything you do. Okay, in a way, no matter what you do, if you don't put machine learning into it, you are doing it wrong. Okay. So this is all very exciting. It definitely makes this field be very exciting to be in. This also, however, comes with certain responsibility. Okay, because as exciting as trying to deploy this ML everywhere, as exciting as it is, I think it behooves of us as a community to stop for a moment and think, okay, is actually the ML technology the way it is now actually truly ready for real-world deployment? Okay, and that's somehow the broad question that we would like to tackle, or specifically, there is many ways to attack this question, and many in the community try to do it. Somehow, the angle that we want to focus on in this talk is something that we kind of phrased as, can we truly rely on the machine learning the way we have it? And even that question has many interpretations. One of them would be that we are kind of afraid that the AI will bring doom to us all. And this is definitely a legitimate concern, but that's not what we want to cover in this talk. What we want to focus on is something actually much more mundane, but because of this actually much more acute and dangerous, is just the fact that essentially we don't really understand yet well how machine learning interacts with other parts of our systems pipeline. Okay? And in particular, kind of whenever machine learning is embedded into a system, it turns out that it gives a way for adversaries to manipulate it in a variety of ways. Okay? And we have seen plenty of examples of that already, but kind of the point here is to just not allow this to happen going further. Okay? So that's when there are some bad guys trying to manipulate our system. That's already where machine learning becomes, like this is a problem for machine learning. But also, even if there is no bad guys in the loop, there is still nature. And sort of when we want to go from 95% reliability to 99% reliability, things actually become quite difficult. And kind of safety is still very much an issue for application of ML. Okay? So this is kind of general theme that we want to tackle here, and I think it behooves for us to just think about, okay, where are these problems coming from. Okay, so essentially, like, why should we worry about all of these questions in the first place? Because we know that a kind of ML seems to work really, really well on all the benchmarks that we deploy it on. Okay, and in particular, here we have one of the key home runs of machine learning, namely the ImageNet challenge. So as all of you probably know, this is like a computer vision object recognition challenge, where you train on roughly 1.5 million of high-resolution images, and your goal is to essentially correctly classify the corresponding test set, well, to place every photo in a correct category. Okay, and over here we have progress over the years, over like how well are we doing on this task. Okay, so in particular we see this market dip in 2012. That's exactly where the AlexNet paper showed up and essentially showed how deep learning can be applied extremely successfully in computer vision, and it just started the computer vision deep learning revolution. And in 2015 something very interesting happened. So essentially the performance of the best performing deep learning system on this challenge actually outperformed humans, or to be more precise, a human, namely Andrej Karpathy. And well, I think Andrej did a pretty good job, and the fact that the existing computer vision solutions can do better than that should definitely give us a pause, and it's definitely impressive. Okay, so that's great. But what I would like us to ponder here is, what does this result actually mean? Okay, so it clearly means that computer vision tools, the way we deploy them now, can outperform humans on this particular benchmark. But somehow, and this is definitely true. This is exactly what this test measures. But somehow, we as a human, we tend to kind of generalize, the things that we see to things that maybe are not there, but kind of we would very much like to see. Okay, and this is definitely the case in computer vision, and there is a good reason for that. Okay, and the good reason for that is something about the conceptual framework that we use, that somehow we kind of sort of are aware of, but don't really think about it. Okay, so what am I referring to here? So let's quickly look back to supervised ML framework, and just let's think about how we think about the process of training a classifier and the way we evaluate it. Okay, so usually we always think there is some kind of distribution in the sky. Okay, that essentially says this distribution of all the objects we could ever see and we would ever encounter, and we would like to classify. Okay, and now, well, the way we train is that we sample a bunch of samples from this distribution, and we just plug it into our training algorithm, and this, this gives us the model that we trained. And then the way we actually check if we are doing a good job, essentially, if we did any good, is essentially what we do is just we sample some more independent sample from the distribution, and then we test, how well our classifiers does on classifying these. Okay, so in particular, our measure of performance is, fraction of mistakes we made during this test. And it's safe to say that we made really, really beautiful progress on trying to optimize this measure of performance. Okay, so everything is great so far, except there is one crucial assumption here that actually is not reflected in practice. Namely, this assumption is that actually in practice it is not the case that the distribution that we use to train our machine learning model is exactly the distribution that the model will encounter where we deploy it in the real world. Okay, so there are various forms of covariate shift, and essentially this almost never happens, that these two distributions are the same. And you might say, well, like that's how we make sense of stuff. We just make assumptions that maybe are not exactly reflected in practice. Still, they lead us to our good solutions. But it turns out, however, that in this case, this may be an assumption that actually was somewhat misleading. Okay, so essentially, what can go wrong in the real world where this assumption does not work, it does not hold anymore? Okay, so I think one of the key implications of this assumption, or lack of this assumption, is the phenomenon that we just observe uniformly, is that our machine learning models, the predictions are actually extremely good on average, but also they are extremely brittle. Okay, so again, one of the most publicized visualization of this is something called adversarial examples. So over here, we have an image of a pig, which state-of-the-art classifiers correctly recognizes as a pig. And so everything is great so far. However, what it turns out is that there is a way for me to add just a little bit of noise to this image. This noise is not random. It's, it's chosen in a very specific way. And the good thing about this thing is that this noise is essentially imperceptible. Okay, so after I added this noise, I have an image on the right. It's not much different to the image I started with. Okay, so to us humans, this is still very much of a pig. However, for some reason now the classifier is convinced that this is an airliner. Okay, so my favorite joke here is that essentially machine learning is truly a magical technology. It can make pigs fly. So that's going for us. And by the way, so this phenomena was probably, if you heard about it before, you heard it from one of these two papers. But again, this is not a new thing to our field. There was a lot of previous work that identified this kind of brittleness. It just somehow, before last 4 years, machine learning struggled even without adversarial noise, and kind of this was not that much of a problem. Now, once the average case performance is here, this worst case performance is what we really realize has to be addressed now. Okay. So this is the kind of the example of a brittleness, but you might say, okay, this noise is not random; it's actually very carefully chosen, and in the lab setting, you for sure can figure it out, synthesize it, and make things fail. But in the real world, there is so many other noise coming from different sources. You don't have such a fine-grained control over what you do. Then probably everything is fine if you just do it in the real world. Like this brittleness does not exhibit itself. However, well, it turns out that there is a numerous demonstration by now that this is not the case, that you can actually deploy this kind of adversarial noise in practice. And I guess my favorite example is over here. So this is just 4 MIT undergrads, or they are no longer undergrads, but they used to be undergrads. Essentially what they did is they 3D printed a turtle that to us, of course, looks like a turtle, but to the state-of-the-art classifier, it identifies as a rifle from very different angles. Okay, so this is something I held in my hand. This is something very physical, and it really does full state-of-the-art classifiers. Okay, so so this definitely is not something that is just of academic interest. This is actually can be happening in the physical world, and in a sense, this goes even worse than that, because. Okay, so far when I talk about this adversarial noise, the noise pattern that I had to add, it was very intricate and complicated. So each pixel had to have a specific values to make it work. In particular, this turtle's pattern on the shell had to be very carefully painted to kind of achieve this adversarial effect. It turns out that you don't even have to go to all these lengths to exhibit some kind of brittleness of our machine learning systems. In particular, it turns out that you just using something like rotation and translations is already enough to see this brittleness. So here is an example. So over here we have just like an image of a rifle, which again is correctly classified with high confidence as a rifle, and everything is great. But now I start rotating it, and as you see, is for some of the angles I actually have the top high confidence classification is a plow, is an agricultural device, and not the rifle. So again, whatever you do, if your object recognition system is not able to reliably recognize the object if you rotate it, then you end in trouble. And by the way, this is not just some kind of quirk of the pipeline. You of course might think of using data augmentation to try to correct it, and and we did try it, and we did evaluate it, and the answer is it helps somewhat, but it definitely does not solve the problem. Okay, so I think we can kind of satisfactorily conclude that the brittleness of ML is a thing, and I guess what we should do now is we should wonder, okay, should we be worried by this or not? Okay, well, needless to say, mine and I'm sure Zico's stand is that that this is a problem, and for a variety of reasons. So the most obvious one is security. Okay, so essentially, whenever I deploy a machine learning system in the context where someone else might have incentive to manipulate it, well, I should be very worried, because if I can make my system see something different than I see, that's exactly how all of the breaches really happen. Okay, and security community had a number of very cool demos showing that this kind of things can happen. So there is a work from CMU that shows that you can 3D print glasses that essentially, once you put them on, the state-of-the-art face recognition system thinks you are a completely different person. Okay, so think about like automated passport gates. You know, now you can just fool them by just putting on some weird glasses. Okay, and by the way, even though in this tutorial we focus mostly on image signal, you know, the same brittleness, everything applies to other type of signal as well. In particular, there is a work from Berkeley by Karlin and Wagner that shows that you can do the same kind of manipulation to sound. So you can kind of synthesize music clips that to you sound like music, but to Alexa or other voice-controlled device, this sounds like a perfectly clear voice command. So you might be listening to the music on radio, and someone might be reprogramming your Alexa, and you will not even know about it. Okay? So this is about security, about like when there are some bad guys to get us. But again, even the safety and reliability is an issue already. So recently, just Tesla, they just released their kind of data from the like object and lane recognition pipeline, essentially as it drives through Paris. And again, it actually is doing pretty amazing job, except you see that these predictions, they can actually be quite glittery and kind of they clearly struggle a bit. And indeed, if you look online, you can see plenty of YouTube video where Tesla drivers, they just record when kind of like situations like here where the driver assistance system, it works great most of the time, but over here it's trying to continue just straight into the divider, and the driver has to take over to avoid like hitting it. And it is even like the system is not even reporting an error. It just thinks really that this is where the lane goes. Okay, so we clearly achieved a lot, but there is more to go. So this is another reason why we should care about this brittleness. But also, there is one more reason why we might want to care, and I usually call it like machine learning alignment. So essentially, adversarial robustness shows us the failure modes of ML that kind of are different to our failure modes. And this should drive the point to us that the way machine learning solutions work and the way they succeed is very different to the way we work and we succeed. Okay, and that's, I think, very important to keep in mind. Okay, so this is all about the brittleness of prediction of machine learning system. And you might ask, okay, is that the only problem in machine learning that we have? And the answer is emphatically no. Okay, so essentially, as I tell my student, every aspect of ML is broken currently if you look at it through the robustness lens. Okay, so far we talked about inference and the problem with adversarial examples, but if you talk about training, there is also a problem looming there. It's called data poisoning. Okay, so what's going on there? Well, essentially, as beautiful and great as ML is, it's actually infinitely data hungry. We always need more and more data to have it perform well. And the implication is that essentially if you need so much data, we can't really afford to be too picky where it is from. So we actually might, train on data we have no full control and we can't really trust. And of course, the question is what can go wrong? And this is exactly the regime of something called data poisoning. And in classic setting, like the goal of data poisoning is just the following, is you would like to coconut a training set by just manipulating some small fraction of it in a way that it maintains training accuracy to be small, but it tries to hamper generalization. So this is the prototypical example. I have two distributions, green and blue, and then here is some sample from the distribution, and that's all I see. And yeah, I find a linear classifier, everything worked great, it's a large margin classifier, it generalizes perfectly. That's the success story of ML. But now if I'm the adversary and I also add this very weird point over here, and then I ask someone to find the best classifier to classify it, well, if he or she does it naively, they will come up with such a classifier, and it will just not generalize, okay? And this is essentially like one of the dangers of data poisoning, that we can get into this kind of being manipulated in this way. So this is essentially like a fundamental problem in the classic ML, and by classic I mean kind of pre-deep learning. In particular, there is a whole robust statistics field that tries to tackle exactly this question. However, it turns out to be not so much of a problem in deep learning, because essentially if deep learning's classifier is confronted with this kind of example, what it really does is essentially memorizes the weird example. So essentially like the classifier you would come up with would look like this, and actually it would generalize just fine. So for some magical reason that we still have to understand better, for deep learning this is not a problem. However, what is a problem is something a bit different. Okay, so essentially, instead of thinking of the goal of trying to hamper generalization across all of the examples, okay, what if we just wanted to manipulate the training set to just affect predictions on some particular set of examples, particular set of inputs? Okay, and when we look at that, then things become actually much, much worse. So in particular, what was shown is that you can just, by manipulating even single example, you can manipulate prediction across a whole classes of predictions later on. But it actually gets even worse than that. So what you can actually show is that you can use the ability to change just a tiny fraction of the data set to essentially take full control over the classifier that will be trained on this. Okay, so essentially imagine that what I have as an adversary later on is when the model is deployed, is that what I can do is that whenever there is an input that I want to have it classified the way I want, not the way it should be classified, all I have to do is I have to just add some planted trigger. And whenever this trigger is present, my classifier, magically, essentially makes a prediction that I wanted it to make. Okay, so this is actually quite scary because, as a user of the system, you don't see anything wrong until I exercise this power. And I think this is something that we should think much, much more about. But I will not talk about it anymore. Today, sorry, not today, on Wednesday, there will be a poster from my lab that talks about data poisoning. And if you want to learn more about this, you should just go there. Okay? So this is data poisoning. But you might ask, okay, so is this training is a problem and inference is a problem? Is that the only problem in machine learning? And as I already told you, the answer is no. So imagine I train my amazing machine learning model, and now I want to deploy it to the whole world. Okay, I would just want to deploy it in the real world and have people use it, maybe pay me for the usage. So everything feels great because now I had my classifier, and it sits on my server. It's secure on the server. I have everything is encrypted. What has to be encrypted. It sounds like everything is great and safe now. Essentially, now nothing can harm my model. In particular, this adversarial noise I discussed about earlier, actually to synthesize it, in principle, I need to have a full access to the weights of the model. So you might say that in this setting, you are safe from it because they cannot access your model directly. So, does the limited access that just corresponds to just having input-output aspect to the model is actually a problem? The answer is no. Okay, and there is essentially the whole kind of line of work on so-called black box attacks that essentially show that just having input-output access to your model is already enough to diagnose. So first of all, to reverse engineer it, and also to diagnose like what will be the perturbations that would mislead it. Okay, so this is not saving us either. So and yeah, I will be talking about this on Friday in one of the workshops if you are interested. Okay, so after seeing all of that, you might start to wonder, okay, so, we've seen some bad things. So, can we try to synthesize, what are the kind of commandments of using ML in a responsible and safe and secure fashion? So what should you do if you wanted to do that? Well, first of all, you should never train on data you don't trust because of the data poisoning. Second of all, you should never let anyone use your model or observe its prediction because they can essentially reverse engineer it and synthesize the black box attack. And also, in the end, you should also not trust your model yourself because of adversarial examples. So I can assure you that as long as you follow these 3 commands, you are just great. You will have a safe and secure machine learning. That's very relieving. But of course, this essentially says that if you want to follow these tenets, machine learning is useless in any of the worst-case scenarios. So this might make us wonder. So are we doomed here? So maybe there is something about ML that makes it really, really nice, where we just care about kind of average case performance. But whenever worst case performance comes into play, it's just fundamentally broken, and there is nothing we can do about this. Okay, and of course, I and many people working in this area believe that the answer is emphatically no. That actually ML can still play an extremely useful and extremely powerful role here. What just needs to happen, though, is that we need to go back to and revisit all the ways, all the tools that we use in the context of ML, and kind of rethink them with this kind of guarantees of being worst case robust in mind. Okay, and even by the way, if you don't really buy into this kind of story of some bad guys being out there trying to manipulate our systems, you still should care about this adversarial robustness because you can view it as a way to stress test your system. So if there is an input that makes your system misbehave, you probably want to know that. Okay, so let's talk about this. And essentially, the rest of this tutorial will be exactly about this. It's just about trying to come up with models that alleviate one of the problems that we just identified, namely this problem of brittle predictions. Okay, so essentially we would like to find classifiers that when confronted with any like small perturbation of a pig, they still know this is a pig, not the airplane. Okay, and that's our goal. Okay, so to answer kind of how can we go about training models that are robust to this kind of adversarial perturbation? Well, we should ask ourselves a question of where do these adversarial examples even come from in the first place? Okay, and to understand that, we have to go back all the way to the kind of the basic tenets of our framework and essentially like think about what is the goal of training as an optimization problem. So what we are trying to do when we do training, essentially we are trying to find the setting of parameters theta that minimizes the loss on our training examples. Or over here just one example, but you can add the sum to generalize from this. And what is nice in particular in deep learning is that our models are differentiable in this parameters theta, so we can use techniques like gradient descent to find good setting of parameters that will make this loss as small as we would like it to be. Okay, again, there is still much to be understood, but at the basic level, at least in practice, that's what seems to be happening. So this is a very convenient thing that this is the problem we are solving, and we can solve it in a very in a fairly principled way. So unfortunately, this is also like the fact that in particular deep learning networks are so convenient to optimize in various shapes or forms is also where this is what you can exploit to synthesize these adversarial perturbations. Because essentially to get an adversarial example, all you have to do is just like look at this problem again and just reparameterize it. So you just freeze the parameters. Let's say you trained good parameters and you are done for now. And now I would just like to find a perturbation of my input that will make the this prediction to be bad. So essentially what it means is just we want to find the perturbation that will make the loss to be large as opposed to small. And the problem is that as much as our system was our machine learning model was differentiable in theta, it's also differentiable in delta. So you can use techniques like gradient descent to find these path perturbations, and that's exactly how the perturbations I showed you earlier were discovered. Okay. So there is, however, like an important question to ask here when we set up this optimization problem. Namely, the question is when I do the optimization, what kind of values of delta should I allow? Okay, and this is an excellent question. And so far, essentially, like in principle, if delta was just a difference between my current example and some other example that is from different class, well, we wouldn't worry about that. That's something that we would like our machine learning to do, just to change prediction if we change the input to a different class. But of course, so this is only interesting if delta is imperceptible or inconsequential in some way. And again, now how to formally capture what imperceptible or inconsequential means? Well, there is a bunch of attempts, but honestly, this is like a really, really hard problem. Essentially, in particular for vision tasks, it would require us to formalize human vision, which we are nowhere close to be. So, so this is definitely like a very important question. It's like what kind of perturbation of the input our vision system should be robust to, and we don't really go into that. I just want to mention that in the rest of the talk we will focus on this LP perturbation. Essentially, when we just say that we are just bounding the LP norm of the change of each individual pixel. So this is a very simplistic metric, but in some ways, it is a metric that we definitely should be robust to before we get anything more complicated. So that's why this is a good kind of milestone to to move towards when we work on the adversarial robustness. Okay. So this is our goal, and now the question is, okay, so this is where adversarial examples are coming from, and now the question is, okay, so how would we go actually about getting models that are not so vulnerable to these perturbations? And in particular, there were quite a bunch of people who essentially claimed when the adversarial examples became a thing, a lot of people claim that this is just an evidence of failure of machine learning, of our machine learning toolkit, that in some way we failed because we let these adversarial examples to arise. Okay? And I think the crucial thing to realize, to understand how to get robust models, is to realize that we did not fail at all. Okay? So adversarial, like the lack of adversarial robustness is not our failure, because it's like the existence of these examples is completely not at odds with our current machine learning toolkit. In particular, what it is that our models try to achieve most of the time, what they try to achieve is something we call standard generalization. So what I would like to do is I would like to, if I sample an example from my distribution that is in the sky, I would like the loss of my classifier on this example to be small in expectation. Okay? So in expectation is great for average case performance, but adversarial examples is a worst case notion. It's actually, it's of measure 0. So this expectation is completely invariant on existence or non-existence of adversarial examples. So in a sense, if we never tried to get, like, essentially if the goal that all of our machine learning toolkit is striving towards is completely invariant over existence of adversarial examples, we should not be surprised they do exist. Okay? So it's essentially, if you wanted to get models where you don't get into trouble with adversarial examples, what you have to do, well, you have to change the goal you are trying to achieve. And the goal that you get, that you should arrive at, is something called, let's say, adversarial robust generalization, in which what you do is saying, oh, what I would like to do is I would like to do well in expectation, not only on the sampled example from distribution, but also on the worst case perturbation of that example. And just like plugging in this max inside of expectation essentially is, is the whole difference between what we were doing so far and what we need to do for adversarial robustness. Okay? So this is, this is the general outlook of what is the problem we are trying to tackle and where we are going from now. So now we know that our goal is the adversarial robustness. Now it's time for taking a deeper dive into this topic. In particular, Zico now will talk in a bit more in-depth about adversarial examples and about kind of ways to figure out how to even check if there exist adversarial examples for our system or not. And then he will talk about actual details of how do you go about training models that are robust to it. And then I will come back a bit and just give you a bit broader perspective again about what can we do with the tools that we achieve over here. Thank you.
All right, is this on? Good. So, as Alex mentioned, after that great sort of broad introduction, I'm going to have the fun job of actually going into some depth about how you do it. So I'll put this down in a second, just 1 second. One thing I actually do want to highlight, which Alex didn't mention, maybe let's try to zoom in here, is that we actually also have an accompanying website for this tutorial. So adversarial-ml-tutorial.org has a set of notes that go through pretty much all the details I'm going to describe here. And so this is the website here. And the notes here are actually in as written as Jupyter notebooks. So there's notes with prose, with examples, but also with code that will do everything I'm going to talk about. So all the examples I have, there's actually code and walkthroughs on how to actually do this. And you can actually download these notes as Jupyter notebooks or just read them on the web and use that to go through sort of these examples. So if anything I do here goes a little bit fast, which it might, please just know you have this resource. We'll highlight it again at the end. It's also, I think, in our Twitter post about this, and you can use that. Okay, so oh, look at that lovely display. Okay, let me quit my. Okay. There we go. All right. So, as Alex mentioned, he sort of gave a broad introduction. And we are, in my part, I really want to emphasize, focusing on this problem of test time adversarial attacks. So, of course, adversarial robustness is much broader than this, but this is the topic I'm going to focus on. And particularly, I'm going to kind of focus on, in some sense, the attack and then the defense. So the first part is going to be about constructing adversarial examples, or maybe a little bit more broadly also verifying whether or not these things exist. And the second part is going to be about training robust models. And in particular, first we'll talk about constructing adversarial examples, doing some verification, then adversarial training, as well as provably robust training. Okay, so as Alex mentioned, the big picture here is the following. We want to train a model, ideally, that is, will generalize well not just on a fixed data set, but actually on adversarial perturbations of that data set. Right? Of course, transportation is not, it's not always easy to do. So of course, what we're going to do in practice is we're going to have some finite data set that we're going to minimize this objective over. All right, so on some data set S, we're going to minimize this robust objective here. And what this portion of the talk is about, these sort of two portions really, is part one is going to be about the inner maximization. So what that means is this is about either finding adversarial examples or actually somehow otherwise verifying that one cannot exist. And I'll talk about what I mean by that in a second. And part two is going to be about training a robust classifier. So how do we solve the outer minimization problem? Now that we've already broken machine learning, we'll tell you how at least we might be able to fix it in some cases. All right. So let's dive into part one now. Here is a view kind of the lost landscape and the problem that we have. Right? So we have some perturbation region delta, that's shown on the bottom there. We have some initial point delta 0, and we have some loss function that exists for different perturbations of delta. Okay? And so if we want to maximize this quantity, what Alex described is just sort of, well, we can just run gradient descent, right? But what I actually want to highlight here is there's other possibilities as well, and actually understanding these things really helps you understand the nature of adversarial examples and verification in this setting. So we really have three options. The first is we can do local search, right? We can just do sort of search to find an adversarial example, and this is actually the most common thing that's done in practice. This is sort of what people typically talk about when we talk about adversarial examples. But there are other possibilities too, and that's actually what I want to really emphasize here is that the other approaches are also possible. So it's also possible actually, maybe not for large models, but for relatively small models, to actually solve this problem exactly using techniques in combinatorial optimization. So we can not just do local search, but we can actually find the worst case example for a given classifier. And finally, we can also form an upper bound on this loss function, at least over the region of question. And if this upper bound has nice properties, like it's convex or really concave because we're maximizing it, we can actually find exact solutions as well that will also let us give verifications of whether or not an adversarial example exists or not. So the first part of the talk here is really going to be about running through these three possibilities and kind of checking what's possible and what's not possible. One thing I do want to emphasize, though, is that all of this work, though it's relatively new in machine learning, and deep learning in particular, it actually goes back a long time to the topic of robust optimization, largely in linear models. And so the only point I want to make here is that for linear models, it actually turns out you can solve this problem exactly, and all those three cases I described before actually collapse to one. So without too much detail here, if we have actually just in this case consider a binary classification problem, it's actually possible to find the worst with norm bounds for your region. So you can find the worst case perturbations. It's just sort of the ones closest to the decision boundary. And actually, sort of formally what this means is that you take your optimization here, you can actually push the max inside the loss because the loss is monotonically decreasing, it becomes a min. And this can be solved analytically in terms of the dual norm of your perturbation region. Right? So this is actually not, I'm not going to go into detail about how this works. There are, of course, a lot more details in the tutorial, but I just want to highlight the fact that this is not a new problem, at least in the context of linear models. This goes back a very long time. Okay, so now let me get to these three cases of how we deal or think about adversarial examples. In the first case, we talk about local search. So, everyone knows, of course, that the loss landscape of deep learning or deep classifiers is non-convex and nasty, subject to local optima. But the great thing about deep learning is we just don't care about this anymore, right? We don't care about the fact that we're optimizing non-convex functions. We're just going to do it anyway, and we're going to try to empirically find an attack that exists within some norm bound. So how do we do this? And there are a lot of ways of doing this, but the main tool I want to highlight, which is actually what Alex mentioned too, are variants of projected gradient descent. The idea here is very simple. We want to optimize our perturbation bound in some region delta, that's represented by the gray region there. And what we do is we just take a step in the direction of the gradient of the loss function. So we're taking a step in the positive direction because we're trying to maximize the loss function. And then we just project back onto the set. So we find the closest point in the set to our projected point. And we just repeat this process, and this is and then we just hopefully we'll find our way to points of high cost. And actually, I would say that most attacks, not quite all of them, but most attacks people use in practice are based on some variant of this, but they're often based upon simplified variants of this. So let me describe actually one. For the most part, I'm actually not going, I'm going to talk about sort of the methodologies here, not specific attacks people have proposed in the past, because I want to follow this general framework of predicted gradient descent. But I think it is worth mentioning one particular type of attack, which was actually one of the ones that kind of ignited a lot of the interest in this field, which is the fast gradient sign methods. This is work by Ian Goodfellow and others in 2014. So the way this arises from gradient descent, at least in our sort of viewpoint, is that we can take now our perturbation region delta to be the L infinity ball. We're thinking about a region where the L infinity norm of the perturbation is less than epsilon, i.e. the perturbation, each coordinate of the perturbation is between negative epsilon and positive epsilon. In this case, actually, projection is very easy. You just clip to the ball. So the projection, that's one reason why this is a nice norm bound. You just clip the entries to the ball. That's the projection operator. And if you think about what predicted gradient descent does in this setting, if you take a big enough step size in the direction of the gradient, you will end up outside the ball, right? You'll end up outside the ball always because there's always some direction. And if you then take a big enough step, you'll actually, and when you project back, you'll actually always be at a corner of the ball, right? So you basically follow this direct gradient direction, you project back, and for a big enough step, you can see you'll always hit a corner. And that corner is just equal to epsilon times the sign of the gradient in each coordinate, right? And that is exactly the fast gradient sign method. It's very nice because it sort of gets you as big a step as you can possibly take within your ball very cheaply, because you only have to evaluate the gradient once, and then you get that step there. So this has become a very sort of popular technique for doing this. All right, so let's see how this actually looks in practice. And I'm going to apologize now to everyone else, because this is 2018, almost 2019, and you're going to see almost entirely MNIST examples in this tutorial. So I'm going to apologize for this in advance. The reason is actually not because these are the best examples to show attacks in, because we know we can attack, as Alex showed, ImageNet. We actually have an example of code to do an attack on a larger problem here. But for some of the defense mechanisms, especially the combinatorial optimization methods, we're still kind of at the scale of ImageNet here. So I want to be very explicit about that, is that a lot of these defense techniques do not yet scale to really large problems. And so, so you also have code that can run this all, and you can run it maybe on one GPU, not, in a few minutes, not days. We are using MNIST here as an example. And in particular, we're going to use two networks, a two-layer fully connected network and a six-layer convolutional network to illustrate a lot of these points. Okay, so let's see what these fast gradient sign methods actually do. And they're also, another thing about MNIST is that these things are a little bit more apparent than they were. You can't even see them in ImageNet, but you actually can see them here in MNIST. Okay, so we're taking our multilayer perceptron, and we're going to adjust the image in a step in the direction of the sign of the gradient using FGSM. And we get an image like this, right? So these things are being adjusted. For now, I'm actually not worrying about there being negative pixels. You can do all this the same thing if you just clip the absolute range of the pixels being between 0 and 1, but these are just numbers as far as the classifier is concerned, so I'm not going to worry too much about that. Do the same thing for a ConvNet. Of course, they're all differentiable, so you can do this, whatever your classifier is, you can still do it. You get something that looks kind of similar, maybe a little less sort of splotchy, a little less speckled noise, but looks very similar. And if we look at the actual test error of these things, so this is the test error on MNIST with a perturbation of size 0.1, which is relatively small, right? That's not going to change our perception of the image here. Then on clean accuracy, these things both do quite well. You have maybe 3% and 1%. Again, these are not even well-trained ConvNets here. We're just sort of running something quickly. And unfortunately, though, when you run this attack method, you get a very large error for both these things. Okay, so this is maybe not good, but the reality actually is this is a really simple method, and we can actually even do better than what I'm showing you here. So the next step is just to actually run this thing I showed you earlier, which is a more fine-grained predicted gradient descent method. So rather than taking sort of one big step, maybe the first direction points you to that corner, but the top right corner, but the top left corner here is actually has higher loss. So you can imagine if you take sort of small steps in the gradient, you're going to end up at a better point overall, right? So that sort of seems intuitive, right? And then once you get to that corner, you sort of start trying to escape, but you just keep getting projected back onto the ball there. And this is the projected gradient descent method, or this invariance are the method. And it's much slower than FGSM because you are taking sort of multiple steps here, but it typically finds better optima for this problem. One thing which I'm going to only mention briefly, which is actually really important here in practice if you do this, is the following. So if you run PGD to run an attack, don't just run normal PGD. Run was actually called projected steepest descent, actually projected normalized steepest descent. So the idea here is that at the actual examples, the gradient of the loss function is often very small. So you have to take a really big step size to get anywhere. But then once you get out of that really small region, you start sort of taking really big steps, then you hit the corner and you kind of reduce to like the fast gradient sign method anyway. And so what we can actually do is instead of taking gradient steps, we actually can just normalize our gradients in the following way. Instead of sort of taking a step in the direction of the gradient, we actually take a step in the direction that maximizes some inner product of the gradient. That's the term V here, subject to some norm constraint on V. Okay, and what this does is this basically searches in some box that's showing here with a dotted line, what's the point in that box that maximizes the inner product of the gradient. And for example, for the L infinity box, that will always be one of the corners. It's actually very similar derivation as we had for FGSM. But what this means is if you want to implement a predicted gradient descent method, you really, and that's all I'll say because we do have some more examples in the tutorial, do this, do steepest descent, don't do normalized steepest descent, don't do normal projected gradient descent because the loss, the values of loss here are very different. Sorry, of the gradient are very different over this region typically. All right, so let's see what this looks like now. We've sort of gone through it in some detail, so we can do things like apply FGSM to that. We can also do PGD. It doesn't look that different, actually. These both fool the classifier into thinking the 7 is actually a 3. But if you look at the actual test error, there is quite a big difference here. So FGSM gets these errors, so fools 41% of the examples on this MNIST classifier, whereas PGD improves that quite a bit. So there actually is quite a bit of difference in practice on this, and this will come back to us when we talk about training robust classifiers. Okay, so 2 more quick notes here. The first one is that what I've described so far is actually what's called an untargeted attack, in that we are just trying to maximize the loss no matter where that puts us. We can also actually try to both maximize the loss of the true class and minimize the loss of some target class to try to fool the classifier into thinking it's actually that target class. And some very nice thing happens here, which is actually going to be the basis for the more complex relaxations, is that if your loss function is something like the cross entropy loss, then the difference of 2 of these loss functions, the first term, the normalization term, actually cancels. And so the actual targeted attack is the same as just maximizing the difference in the class logits. That's the output of the linear layer of the classifier over the 2 classes that you have. Right, so this last formulation here is actually equivalent to doing that, and this is sort of an important simplification we can have. Okay, so let's see what this looks like. We can take a step. If we maximize, take this 7 here, we maximize the 0 class, the probability, or really the logit, the linear term of the 0 class minus the linear term of the 7th class, and we get the 0. If we do the same thing but with a different loss function, maximizing the linear term on the 2 class and minimizing it on the 7 class, we get the prediction 2. Now, one sort of note here is that we might succeed in fooling the classifier even if we don't actually achieve the class we want, because the best way to minimize, say, the 2 label might be to actually minimize the 1 label even more, right? So we might not succeed at changing the class to our target, but we will succeed ideally in creating an adversarial example. And the last thing I want to say about these sort of local search attacks is that we can do them in other norms too. So I showed everything in terms of the L infinity norm, but everything we've done here, right, the steepest descent, everything, normalized steepest descent, everything like that, can be derived just as easily for other norms, for the L2 norm, for the L1 norm, sort of for the L0 norm, that's a little trickier, and it all works. So for example, L2 attacks tend to have more mass in certain regions and less sort of spread out by the nature of the norm itself. Okay, now the last thing I want to say, since I'm talking about attacks here, is that you might be asking, what about all these things I've heard about of these different attacks people have proposed, because there's been a lot of papers in it. And with apologies to people that have proposed a lot of these things, there's actually some in the audience I know here, so we'll see how they feel about me afterwards. But I think, and these papers are of course really important because they were the first to study these attacks in some detail. But I think we're actually at a point in the field where it's more valuable to describe the attacks in terms of the perturbation bound you're allowing and the optimization procedure you're using to optimize that. Right? This is sort of an opinion now, but I think this is a more clear description than relying just on the name or the publication that proposed this, because it isn't always clear then what's actually being done here. Okay, moving on now. This has been the most common way of solving this inner maximization problem, but the thing I want to highlight here is there are other ways as well. So in particular, we actually can solve this exactly. We're actually going to solve the targeted attack version exactly using combinatorial optimization. And so to do this, I want to actually dive into a little bit of detail here and throw up a little bit more mathematical notation to form the adversarial attack as an optimization problem. All right, so you can write our network, and I'm actually going to be explicit now and say we have, say, a multi-layer ReLU network. So our input to the first layer, Z1, is just the input X. And after that, each layer is the ReLU of some linear function of the previous layer. And our class logits are a linear function of the previous layer, of the second to last layer. All right? So we don't apply a ReLU or even a softmax to the last layer. It's just the logits, it's pre-softmax. Okay? So now we can actually write a targeted attack as an optimization problem. It's not an easy one to solve, but the point in part, this is an optimization formulation of how we think about attacking classifiers. All right? And the idea here is we're going to minimize the unit basis on the true class minus the unit basis on the target class, the inner product of that thing and the last layer, which are the class logits. So again, all we're really doing here is we're minimizing the class logit of the true class and maximizing the class logit of the target class. All right? And this is just notation for that. So it's important to kind of keep in mind. I'm going to switch this connotation, so it's important to kind of keep that in mind. Subject to now our ReLU constraints, right? We have to have our next layer be the ReLU of the previous layer of a linear function of the previous layer, and some norm-bound constraint. Okay. So the problem here is that this is not a problem that can be solved by any sort of normal optimization optimizer, right? It has a nonlinear equality constraint in it, and of course, this makes it a very hard problem. But the key point here is that although it's a little hard to solve, and this is one thing we go into a lot of detail with in the notes, is that we actually can write this problem equivalently in a form that at least can be solved by standard combinatorial solvers. So things like integer programming solvers, which has been done by us as well as some other people in the past, as well as things like SMT solvers. There's a lot of work on using SMT methods to solve these things. Now in practice, off-the-shelf solvers, these are things like Cplex or Gurobi, if you've heard of those. They scale maybe to about 100 hidden units. So we're talking about really, really small networks here, just to be clear. But you can get a reasonably performing like MNIST network and actually verify it formally, which is kind of cool. You can actually can check, for an example, what's the worst you could do on any given task. One of the key challenges of this actually ends up being actually just computing element-wise bounds on the activations. So you need to be able to basically compute lower and upper bounds on the linear terms before you go into the ReLU. This is actually going to be a thing that comes up later also when we talk about convex methods. So I just want to mention this here briefly. It's actually quite easy to come up with simple bounds on activations. So for example, if I have some activation Z where I have an upper and lower bound on that, and I want to upper and lower bound a linear function of that, I can just take the positive and negative parts of my W matrix and do it this way. But the actual thing here the figure's a little better to show this. What's really happening here is we're propagating intervals to the network. So if you just run the point through the network, it produces some output. But if you actually think about a region around that point, that region will similarly propagate through the network and really typically grow in size as it goes through the network. So that's all we're doing here. We're forming these interval bounds to kind of show what sorts of regions you can achieve with our classifier. That's going to return when we talk about convex relaxations. All right, so the last thing I want to say here is just talk about the fact that we can use this technique to certify robustness, of course, of a classifier. And actually, we don't even need to solve the problem. We don't even actually need to find the, or know about, I mean, we need to solve it. We only actually need to even know what the solution is. All we need to know whether we can certify an example or not is the objective value of that solution. So let me sort of go through that, what I mean by that. So remember, our objective that we're trying to optimize in the optimization formulation of these attacks is the following. We're trying to minimize the class logit of the true class and maximize the class logit of the other class, some target class. So if I solve this problem and the result is negative, that means the target class's activation, right, probability, is higher now than the true class. And so this means we have an adversarial example. On the other hand, if I solve this same thing and I found my objective value is positive, this means that there is no adversarial example at all, right? Because the class probability of the true class is still higher than the probability of the target class. So there's no method, can't come up with any that will change the label of this example. So just to illustrate here, if we have a 7 here, say we solve some problem where we're trying to have a targeted attack on the class 0, so we're minimizing the logit on unit 7 and maximizing it on unit 0, and this is negative, that means we have an adversarial example. It actually doesn't still necessarily change the class to be a 0, but it's an adversarial example. Whereas if we do something like this and we find that we're now trying to minimize or maximize the logit on class 1, and this is positive, then we actually know there's no adversarial example at all that can make this classifier predict class 1. Okay, so this is the sort of fundamental ideas, and we actually have some code you can play with where you can use an integer programming solver to formally verify at least some small networks, but still still MNIST sized networks, not ImageNet sized networks. Okay, so lastly, before I sort of move on to the next section here, I want to talk about convex relaxations. This is the third point. So we talked about sort of local solutions, those are sort of lower bounds than subjective. We can also talk about exact solutions, and finally we can talk about convex relaxations, which provide upper bounds on the solution to this problem. Okay, so how do these convex relaxations work? There are actually several ways you can do this. One of them is based essentially on relaxing the integer programming formulation of the verification procedure. So the idea here is that the integer programming formulation had these hard constraints that basically the post-activation had to be the ReLU of this previous layer's linear function, right? Within some bounded range, actually, because we actually had an upper and lower bound that these could attain. Now what we can do instead is replace that non-convex set with its convex relaxation, which means that the next layer and the previous layer, they don't lie on the ReLU anymore. They now lie within some relaxed linear set. And the cool thing about this is that if you relax the integer program this way, and it's actually a very sort of simple, straightforward relaxation of the linear program, of the integer program, you get a linear program now. And linear programs, there actually are efficient polynomial time methods for solving them. So unlike combinatorial optimization, we actually expect that we sometimes can really solve these things. Okay, so a quick sort of note on this. Another way of sort of viewing this is that if you take the norm ball and sort of feed it to the network, that first figure there shows kind of some complex shape. And what we're doing effectively is we're relaxing that shape. We're thinking about an outer bound on that shape that gives us more freedom in choosing effectively our adversarial examples. Now, what this means is that the objective of a targeted attack for the linear program is going to be actually a lower bound on the objective of the true thing. And this will come in handy in a second when I talk about certifications. So they actually can still be used to sort of prove sometimes that no adversarial example exists. Of course, solving the LP is kind of slow still, and so fortunately there do exist fast methods based upon things like convex duality for approximately solving that LP. But what I actually want to highlight even more than that is an even faster method, which some recent work has been showing is competitive with these more complex relaxations. And that is just interval-based bounds. So I showed you before sort of how we propagate interval bounds, or at least I alluded to how we propagate interval bounds to the network. It turns out if you sort of take those interval bounds, we now have a known region that the last layer of the network can lie in. And if we throw away everything else from our network, we still can actually get a bound on how much I can sort of decrease, say, my targeted attack, right? There's just an analytical solution to this, and you can solve it kind of exactly. Here it is if you really care, but the real point here is that I can also use just interval bounds to provide an even looser relaxation of the problem. Okay, so I've sort of said a lot here in the last two sections, and I kind of want to pop back up now for a second and highlight what the real value of all this is. Okay, so if some of that was a little bit into the weeds for you, don't worry about it. We're going to sort of pop back up a little bit right now, and then when we talk about training, we'll actually give some sort of examples of how these things really work. But here's the high-level thing I want to give. I sort of want to show you. So say we have our trusty digit 7 here. This is the first example of the MNIST test set, by the way. So this is why it keeps appearing here again and again. And suppose I solve my verification problem using the binary integer, you see the integer programming formulation of my exact verification procedure. Okay? And if that result gives me a negative solution, then I know that there exists an adversarial example. Right? In this case, trying to make the thing class 0, because I'm minimizing the class 0, maximizing the class 0 logic, minimizing the true class logic. If, on the other hand, I do the same thing with the convex constraints, I will also get a negative number, because that one will actually always be lower than the first one. But importantly, the fact that I have a negative term here doesn't actually tell me anything. I don't know that an adversarial example exists or not, because I've relaxed the set of allowable sort of activations I can achieve. And so the fact that I can achieve kind of an adversarial example in this relaxed set doesn't actually tell me anything. On the other hand, and so for finding adversarial examples, these convex relaxations are actually quite not very useful. They don't really provide much in that regard. Fortunately, though, we sort of don't have that problem. We already know how to construct adversarial examples pretty well, just using gradient-based techniques. What we really don't know how to do well with these gradient-based techniques is verify that no such example can exist. And the nice thing about these convex relaxations is that if we solve the same problem, say trying to make the class label look like a class label 1, and get a positive number. So in other words, what that means is the class logit, the class probability of the true class under this relaxed attack is still higher than the class probability of the alternative class, the target class. What I now know is that there's actually no adversarial example for this class. So I've actually managed to verify that no adversarial example exists, and do so in a way that only involves convex methods. So that's very nice, because these things are actually solvable, and we actually sometimes cannot just get attacks, but we might be able to actually get proofs that no attack exists. Okay, so that actually covers now the 3 main techniques we have for dealing with that inner maximization problem. And now I'm going to pop back out, and start talking about training models, not just testing them. So let's take back to the big picture here. What part 1 was all about, really, was creating adversarial examples, right? So how do I solve that inner maximization problem? What part 2 is going to be about is how do I train a model that somehow is robust to these adversarial attacks? And it turns out that actually the strategies I had before will exactly lead to methods for training. So we're now moving from just the outer minimization, inner minimization, maximization, to the outer minimization. And if we think about the techniques we use for search here, using our local bounds naturally leads to a procedure that we call adversarial training. So this is also sort of advocated by Ian Goodfellow and others, and I'll describe what that means in a second. We can't really use combinatorial optimization to train models. It's just too slow. It takes on the order of minutes or for big enough models, until the heat death of the universe to verify them. So we're not going to be able to train, models ever, well, maybe really small ones, but not larger ones, using combinatorial optimization. We can, however, train models based upon our convex relaxations, and these will lead to provably robust models. Models where we can say, not only do they seem to perform well, but it actually can guarantee you that no attack, no test time attack, is going to fool this classifier, at least within a certain norm ball. Okay, so let me start, first of all, talking about adversarial training. The idea here is that how do we go about optimizing this objective? How do we go about training a model that optimizes, that minimizes over our model this sum of robust, adversarially robust losses? Now, we would like to be able to optimize it with gradient descent, the way we optimize everything in deep learning. But how do I take the gradient of that term when it involves the maximum? Well, sort of very nicely, it turns out there's a really nice answer to this, and it's called Danskin's theorem. So the idea here is very simple and intuitive, but it's actually a very subtle point, is that if I want to take a gradient of this max term, that's the inner term that I'm trying to optimize here, what I can do is I can just find the optimum in that, over that set, and take the gradient at that optimum point. This sounds obvious, and I thought this was obvious, but actually, for general optimization, this is a really subtle result that takes many, many pages to prove. In the convex case, it's not quite so bad, but this is actually a pretty subtle result. But it's really, really nice, because it means that in order to solve our outer optimization problem with gradient descent, we don't need some sort of fancy new procedure. All we really need to do is be able to find adversarial examples and then optimize from those positions. Now, or optimize our parameters at those points. Now, it turns out actually that I should have sort of a big asterisk here, because this only applies when we perform the inner maximization exactly, which brings us back to the combinatorial space that we don't want to deal with. But now, of course, we have deep learning to the rescue, where let's just do this anyway, solving our inner optimization problem sort of empirically, and not caring about the fact that we're not really in the regime of true theory here in Danskin's theorem. And this leads to exactly kind of the standard adversarial training procedure advocated, for example, by Ian Goodfellow in one of the original adversarial example, or one of the many papers released that excited people about adversarial examples. So the idea here is very simple, and all it really involves is that instead of training at the actual data points, you train at the worst case perturbation of those data points, right? So I select a mini batch. For each example in a mini batch, I find the worst case perturbation, and then I update the parameters based upon the gradients at those worst case perturbations. That's actually all I do in this whole process. And I should say it's also sort of common to sometimes mix robust and non-robust updates. So you might take some gradient steps with the original examples, some with the robust at the sort of worst case examples. But really, you can actually just take the worst case ones too, and this still works okay. Okay, so let's see how this works now. So remember, we had our old ConvNet, which we trained sort of with normal training, and it did really well on standard error here, but it actually did a lot worse on, if we attack it with the fast gradient sign method or with PGD, predicted gradient descent, it does much worse. So the nice thing is that if I now train my same exact architecture using this method on the right here, we actually get a much more robust network, right? So now, if I train it on this attack, it only suffers about 2.8% error on this. Now, this seems good, right? And actually, I think Alex touched on this a little bit, and I think he may touch on that some more later. But we have to be really careful about declaring success right now, right? Because what I'm doing in my evaluation here is I'm evaluating the method on the exact same attack that I trained it on. And we know deep learning is really good. When you give it something, it's really, really good at doing that. All right, so it's really good at optimizing exactly what we tell it to optimize. And this has actually been sort of the challenge for a lot of adversarial examples in the past, is that we have to be sort of careful. So, however, here's what I will say. To the best of our empirical knowledge, models trained in this fashion with a strong PGD, so using basically predicted steepest descent, so a normalized type of PGD, with additionally some random restarts in the PGD process, seem to be robust to any empirical attack we can throw at them. So if I run the same thing, maybe say with more iterations of PGD, with more randomization, all this kind of stuff, I actually don't increase my loss that much. And in fact, Alex's group, they posted a model they trained, not this one, but actually a more complex model they trained in the same fashion. And people really haven't been able to attack it that much. And the crux of the issue here is that we are trying in this PGD-based training to really do as good a job as we can of solving that inner maximization problem. And so when we do that, we actually tend to get classifiers that appear to be pretty robust to anything we can throw at them. At least that, the error that PGD gets is about the same error that any other attack we can really formulate gets, with some, maybe some minor improvements at the margins. So it looks good, but we should really be careful before declaring it a success. And so actually, we have this model again in the notes, and you can try other attacks. But I actually think for this small data set, this is probably actually a pretty robust model. Again, for a pretty small epsilon, this is a perturbation of L-infinity perturbations of size 0.1. But one thing I want to actually emphasize is that what we shouldn't do, or what's not particularly informative, is to evaluate against different types of attacks, like taking an L-infinity trained model and evaluating it against L2 or L1 attacks. Because of course, the model is trained on one attack. It's not going to generalize. We'd also know that, right? And if you want to have if we want to protect against L1 or L2 attacks, we should just train against L1 or L2 with L1 or L2 PGD. If you want to have some notion of generalizing to, say, new attack modes, right, new sort of general perturbation sets, we're not quite there in the field yet. You would need to sort of define some notion of some set of allowable perturbation regions and sample from this and then try to generalize the new ones, and we're not there yet. So I just want to add a final note there. It's really not informative to evaluate these models against other threat models. If you want a model that will defend well against L2 or L1 attacks, just train a model against L1 or L2 attacks with the same PGD method. Now, another kind of fundamental question is what makes these models robust? Why are they robust? And one way to look at this is actually by looking at the cost surfaces of these models. So what I'm showing here is actually the loss surface projected along 2 dimensions here, including the adversarial dimension. And if we take our standard training, that loss really is quite steep. So very close to the point. This is all within an epsilon ball of 0.1 for MNIST. There's a lot of directions of really, really sharp increase. Whereas the loss surface of the robust model, and the important point here is actually the scale on the right. I don't know if you can see that, but it's basically, the bumpiness here is just sort of numerical things. That really what's happening here is that this is essentially a flat surface. So it seems like when we train these things with PGD, we genuinely get loss surfaces that are quite smooth and flat. They don't seem to have these big peaks, and that of course means that they're not going to be susceptible to these adversarial attacks. Now, of course, we can't verify that along every dimension, right? That's the whole point, is that we can't check every possible corner of this 2 to the n corners of the norm ball, but we can get some sense by looking at these kind of figures and looking at the loss in this way. Okay, so this is the sort of, in some sense, the best way we know how to train our empirically train models against attacks like this. And while the jury is, of course, still out whenever you have a method that's only empirical, they seem to hold up really well against possible attacks. So the natural question is, we have these seemingly robust models. And in the last section, I also described to you some tractable, convex ways of verifying whether a classifier is robust or not. Let's see if we can take these robust models and actually verify them. So let's use the convex bounds. In this case, we're going to use those interval-based bounds. It's the simple one I described at the end, to see what sort of level of adversarial performance we can guarantee for the robust model. OK, so here we go. Here's the big reveal here. So clean error for both the ConvNet and the robust training ConvNet is about the same. course, FGSM attacks do much better on the robust, or on the normal, or are able to fool the normal model much more than the robust model. PGD also fools the normal model even more. And the question, of course, is what's this robust bound going to tell us? You know, maybe it probably can't tell us anything about the normal convnet, but maybe it can tell us something about our robust model we trained. And unfortunately, the actual robust bounds you get if you run the convex procedure for both these things is completely vacuous. And it's not just almost vacuous, it's like really totally vacuous here. Like, I think you have to get epsilon down. So this is an epsilon of 0.1. I think to get a reasonable bound, you have to go to epsilon 0.0001 or 0.0002 or something like that. It's, you're not getting anywhere close with these kind of things. So what's happening here? Why, you know, we had this great thing, but that we can prove about models, but it doesn't give us anything useful. Of course, if we could solve the IP about these things, then we might have more stuff, but actually this model is too big to solve the integer program for. That would take, I don't know about the heat death of the universe, but it would take a really long time, at least in my implementation, to solve this. Okay, so what's going on here? And the key insight here is that models that can be convexly verified are a small subset of what seem to be the actually robust models, right? And so if you think about sort of the Venn diagram here, there's all models, including non-robust ones. There's some space of robust models in that. And then within that, there's some space of convexly verifiable models, right? Maybe. We haven't actually proven whether that's empty or not. It could be empty, but stay tuned for that. And it turns out that these convex bounds, sort of the tractable, provable bounds that we have, are very loose unless the model is built specifically with them in mind. All right, so it's great that we have these bounds, but in order to actually get them to say anything non-vacuous about classifiers, we actually need to train models upon them. So this is, in fact, bringing me towards the end of what I'm going to say here, because it turns out this is possible. So the convex bounds I described, so like the interval bounds, those notions of propagating a box through the network. This, just like a normal network, is actually also a convex function of the network parameters. So it's a function of the weights and the biases and all this kind of stuff. And well, I won't go back to that, but it basically involves maxes of these things and zeros and the positive and negative parts, et cetera. But it's still just a differentiable function of the network parameters. And what that means is my final bound that I have, my final convex bound I have on these things, is also a differentiable function of the model parameters. So I can use these to actually minimize not my actual robust loss. That's very hard. That's sort of a combinatorial hard thing. But I can use this to minimize an upper bound, a strict provable upper bound on the on the robust loss of a classifier. Of course, the actual outer optimization procedure is still not convex, but at least we have a known provable bound. And actually, some recent work kind of surprisingly shows that interval bound propagation actually can sometimes work better for this than more complex approaches even, though I think the jury is still out on exactly what level of complexity you want for your training versus for your verification. Okay, so let's see the final thing here I'm going to show before we will pop much further out again and talk at a higher level. And there should be time for questions at the end too. If I think we'll finish before 10:30. Okay, so here's our different settings here. This is again showing test error, the attacks of the different things, as well as the provable bound. Our convnet, gets bad in all regards except normal clean error. Our robust convnet we trained with PGD works well in all the empirical attacks, but the bound itself is completely vacuous. But finally, if I actually train the network to minimize this bound, we get the following. So this is just a quick one that we have again in the notes. You can do much better than this. You can get this down, at least on MNIST, quite low, but I don't want to actually make it too low because that will give a false impression. You can do that on any data set, and other ones is much harder. But at least on MNIST, you can get these down pretty low. And so what we have here, it's not going to win any awards by any means. But what we have is an MNIST model where on the test set, I know that no matter what attack I have, no matter how many more papers are written about attacks, no matter anything, no one's going to have higher error, higher robust adversarial error with a lot of qualifications here, right? With L infinity perturbations under epsilon of 0.1. no one's going to ever reveal a higher error than 9.7 on this classifier. So that's nice. It's something we couldn't do, didn't know how to do even a little bit more than a year ago. And these techniques have now really been growing a lot within the machine learning literature. And so we're coming up with a lot more techniques for verifying them things as well as training these verified models. Okay, so one last note from me before I throw it back to Alex. And that is, these results seem good, right? It seems promising here. I had a bad normal model. I trained a robust model. Everything looked good. I could even train a provably robust model to get maybe a little slightly worse accuracy, but still pretty good accuracy, and things seem really good. However, one thing I should emphasize is that these sort of promising results, at least currently, are to a large extent actually more a function of MNIST than a function of our ability to scale these things to really big problems. All right, so MNIST is also actually quite easy to secure against attacks because it's kind of a binary problem, right? If there's pixels that are on or off, and adding a little bit of noise here and there doesn't really make things that much harder intuitively. But for example, like CFAR, the best bounds that we know of, the best empirical bounds that we know of, which CFAR is solved to like 3% error currently, maybe even lower now. CFAR 10 this is. On CFAR 10, the best empirical bounds we know of say that the error is, we can't find an attack that gives, with actually a pretty small perturbation, about smaller than the one we showed for MNIST there. We have a guaranteed bound of, we can achieve 53% error with the best methods that we know how to do. And the provable bounds, that's what we can do is say there's about, we know we can form a model that has less than 70% error on CFAR. Whereas again, the state of the art now is around 3%. So for larger problems, scaling these things up and finding the architectures, both the architectures, the bounds, and the optimization procedures that will make these things work is still very much an open question. And it's the topic of current and ongoing research, both in the empirical attack side and defense side, and in the provable attack and defense side. So next up, Alex is going to talk a little bit more about this, as well as a higher level of issues that arise from these adversarial examples.
Okay, so welcome back. Thanks, Zico. This was really nice. Even I learned something. So far Zico provided this excellent view into kind of, the nuts and bolts of how do you diagnose robustness, how do you ensure robustness, and where we are. But somehow, I think what we both feel is very important here is not to miss the big picture here. That essentially, again, security and ensuring the security is very important. But there actually is something even kind of a bit more high level that is going on here. So sort of like that the adversarial robustness might be, it's an interesting notion by itself, even if you take it outside of the context of security, okay? So just to remind, so essentially in some ways, this conceptual picture that emerges here is that kind of we can try to not only focus on the applications of ML that require security, but actually once we know that there are applications where we care about this kind of security aspects of ML, we can take a step back and look at machine learning and see how does machine learning look like through this lens of robustness, okay? So specifically, if I, on one hand, take this standard machine learning that we are doing now, which corresponds to standard generalization, how does it differ from this kind of robust machine learning that we might trying to build here? So essentially, on the very mathematical level, all that we are trying to compare is these two fields. One that tries to maximize, to achieve the first goal, and the other one that tries to achieve the second goal. And one thing that I really want to emphasize here, that should be already clear from what Zico's talk, is that really, even though we sort of discovered, discovered in quotes, the adversarial examples in the context of deep learning, it's really not only a deep learning problem by far. Yes, in deep learning, it's easier to find adversarial examples, but every type of classifiers that we know of has them. Why does it have them? Because, again, it was trying to achieve standard generalization. It never cared about robust generalization. So, if we never design for it, there is no reason for us to expect that magically things happen. Okay, so that's just some point to keep in mind. But yeah, but this is the question now. Okay, saying we have these two different notion of machine learning or succeeding in machine learning. What does change when we move from one to the other? Okay, so I will just give you some vignettes. So the first one is just about like overfitting of robust deep learning. Okay, so we all know the story, especially for deep learning and in general classic optimization of overfitting. So over here you can train some classifier. And yes, like this is the training accuracy. So after pushing it for long enough, we get 100% training accuracy. And of course, so that's what we do in our tools. But of course, the question is, okay, how, what will happen if we actually test the solution on the, on the unseen test set? And this is the usual performance that we observe. And what is sort of amazing, especially for deep networks, that actually the gap between what we can ensure by training and what we actually also get on unseen samples, the generalization gap tends to be really small. Okay, so that's great in the standard machine learning, but how does it look like in robust setting? Okay, so in robust setting we also, well, it's much harder, as Zico explained, to actually get to this like 100% robust training error. Sometimes even impossible because of data being not of perfectly separable. But yeah, we can get there. And now, in particular, this is a picture that we get for CFAR. So that was exactly what Zico mentioned at the end. So this is this picture for CFAR. So we can train a classifier that gets 100% robust training accuracy. So there exists a classifier that is robust. However, if we look what happens on unseen examples, that's the performance we observe. So we have this really huge generalization gap. Okay, so essentially the thing we get is that we really get under 50% robust performance, even though the training performance is 100 or close to it. Okay, so well, what can we do? The obvious idea that we know from standard machine learning is just to use regularization, and maybe this idea does work. So far we tried, and unfortunately, even if it seemed that it might work, it doesn't. So this is actually quite puzzling for us, especially because we tried to push the CFAR as in our lab quite a lot, and started to wonder, okay, maybe there is some inherent reason why getting better accuracy and kind of avoiding overfitting is a problem here. And indeed, there is some phenomenon that we discovered, and the phenomenon that we discovered is that actually it turns out that if we think about aiming for adversarial robust generalization as opposed to standard generalization, then actually it's not only a matter of the optimization problem corresponding to training becoming more difficult, it's also the kind of sample complexity of this problem becomes worse. So in other terms, essentially we tend to need more data to even be able to get a robust classifier, so a classifier that generalizes in a robust way. So here is just the kind of theorem that you can actually prove. You can essentially prove that there exists, in D dimensions, some even very simple distributions, extremely simple distributions, that already exhibit this effect of, if I just have one sample for distribution, I'm already able to get a very good classifier that performs extremely well on average sense, in an average sense. However, in order to have any hope of building a robust classifier, I need to see many more samples. Okay? And the key here, you think that this is like information theoretic bound, so it doesn't matter what you do. You can do data documentation, whatever. Essentially, you will be stuck until you have seen enough samples. And you will be not able to get any meaningful, robust classifier. Okay? So as I say, these distributions are really simple. So one of them is just like a simple, hypercube performed, perturbed distribution. It's essentially kind of models what's happening on MNIST, where linear classifiers for robust, robust classification require a lot of data. But essentially, if you are able to use a nonlinear classifier as something called thresholding, if you think about how MNIST works, you can very easily get a robust classifier. But then there are also other distributions. So the first distribution was hard for linear classifiers, but easy for nonlinear classifiers. But you can also connect, distributions that are hard for any classifier. So essentially, no matter what classifier you use, unless you have seen enough samples, you will not be able to get robust classifier, even though, average case, like the standard generalization is very easy even for one sample. Okay, so that's all I will say about this. There is actually a spotlight and poster about this on Tuesday. But yeah, so that's one effect in which kind of the sample complexity of the problem changes often quite dramatically. But there is also another issue I wanted to highlight is sort of the question of, how does being robust affect our standard generalization. Okay, so somehow where I'm coming from, so somehow my belief coming into working with this was that somehow once you really do all this work and put all this work to get a robust classifier, then it should be kind of superior to a standard classifier in all aspects. Okay, so in particular, we know that one of the effective techniques to get a better standard generalization is data augmentation. It's essentially like adding some transformation to your training data during training to essentially kind of you try to impose a stronger prior, and indeed works very, very well. And in some ways, if you look at adversarial training, which is the current leading technique to get robustness, you can view it as an ultimate version of data augmentation. Because essentially what you are doing, you are always training on the adversarial perturbation of the training data. So in some ways, you are training on the most confusing version of the training set. Okay? So clearly, you would expect that, essentially this is only a good thing, and in particular, that being robust can only make your standard generalization even better, because you are using this kind of implicitly, this ultimate way of doing data augmentation. And well, let's look at the data. So yeah, over here we have just the the standard test accuracy of a standard model trained in the standard way. So this is just a reference point. However, if we take a look at what happens if I just look at the standard accuracy of a robust model, then we see that there actually is a gap. It's not a big gap, but it is a gap. It's actually a consistent gap, and yeah, we tried it in a different setup. Normally, by the way, there is a regime, like a very, like at the very beginning, data augmentation, robust training sometimes does help a little bit, but in the long term, when we look at the regime where actually we end up training, it's always consistently lower, okay? So what's going on? So where is this consistent gap coming from? Why, why we seem to be inferior in this way? And in a sense, as many things, in the retrospect, it's clear what's going on. So first of all, there is this phenomenon that kind of, if I'm trying to train a classifier, I somehow have to choose if I want to maximize this standard generalization performance, or do I want the classifier to be robust? And there is actually an inherent trade-off between this. And again, the trade-off actually, in the end, is kind of pretty clear. What is the key idea here is sort of, if you look back at standard training, and just when your goal is just standard generalization, then to you, essentially, any feature that has any correlation with the correct label is useful to you. Okay, so you can always milk it a bit to get even better standard performance. However, in the robust setting, you can't just, if there is some feature that is maybe very weakly correlated with the label, but kind of it's easy for the classifier to perturb, well, then you have to actually make a call if you actually want to take advantage of this and improve your standard accuracy or not. Okay, and this is the basic kind of trade-off at play here that kind of manifests itself. And yeah, you can imagine this is just like a simple way to think about it. That yeah, I have a data set in which like the first coordinate is strongly correlated with the correct label, but it's not perfect. And then I have a bunch of very weakly independent correlated labels. Features that are the rest of my that are in the rest of my data set. And somehow, what will happen is that these weakly correlated features, all of them, if I aggregate them, they aggregate to a very, very meaningful and predictive, meta feature. But the problem is that in standard training, what you will do, you will just use this meta feature to get essentially perfect classification. However, in the robust setting, you are not even really able to kind of to take advantage of all of these features, because even though they are very accurate on average, they are very easy to be manipulated by the adversary, because the correlation is only, each one of them is only weakly correlated with the, with the correct label. Okay, and this is essentially the, the explanation here. Okay, so let's just try to summarize a little bit, where we are, where we think about this difference between robust machine learning and the standard machine learning. So it's very clear to everyone, and that's what is expected, that there actually is a price to being robust. Okay, so in particular, as we already said, as Zico said, first of all, optimization the optimization problem that we need to solve during training is way more difficult, and also the one other thing that we discovered is that the models have to be larger. So this is clearly and undeniably a bad thing. We also just mentioned that actually you might also need more data. So it's not only about training time or size of the model. Also, you might need more data to train. And also, as we said, is that actually you might also need to kind of give up a bit on standard accuracy. Okay, so this is something again. So what we observe, and also there is a more recent work by Bubek et al. That kind of tries to make this point even more broadly. So so there are all these costs, and that's somehow to be expected. It seems we are trying to get something stronger, so we have to pay for that. But it turns out that there are also somewhat unexpected benefits. Like, essentially, like beyond just being robust, it turns out that robust models kind of have additional features that might be desirable. Okay, so one of the things I wanted to highlight is in some ways, the robust models tend to be more semantically meaningful. Okay, so what does it mean? I will just give you an example because honestly, we still don't really understand what's going on there. So, one so what is the going back to? Yes, like it's going back to this fact that all of you are probably aware of is that, as amazing as, technology like deep learning is, it's sort of very black box, and that's a big problem. In the sense, like, when I have a classifier, if I plug in the input, I will get an output, and this output will be mostly correct. But it's very hard for us to make sense why this output was made on this input. Okay, and that's there is a whole field of machine learning currently trying to kind of help us with this problem. In particular, one of the most basic ways of trying to make sense of what, let's say, deep learning classifier, why it made the particular decision on a given input is something called saliency maps. So essentially what you do is that whenever I see an input, what I look at each pixel, and I see what is, how sensitive the prediction is on, to changing just this pixel around. Okay? And then what I do is I just essentially construct this heat map that the color of a pixel is more intense, the more influential it is. And so that's a great idea. And now, however, when you do it just to a standard model, right away, you will get pictures like this, which are somewhat informative, but also show that this model is not exactly doing maybe what you are thinking, that you would expect. In particular, prediction seems to be also influenced by things that are just artifacts and not something that will actually, that you actually tie to the correct prediction. And of course, there is a whole industry of very interesting tools to make the saliency maps even better. Take them from this kind of saliency maps to make them much more, nice. But what we discovered is that if you just do the same experiment just to the robust model alone, okay, so you just impose L infinity perturbation. So you just say that the image classification should not move if I just change each pixel by just tiny amount. Then suddenly you are getting this kind of saliency maps right away, with 3 lines of code. You just get this, okay? And this clearly looks much more closely to what we as humans would expect to happen. And this actually gets even more fun. So in some way, what robustness does, it aligns the loss landscape of the model, again, more aligns it more with our semantic understanding of the problem. So let's do another experiment. So what I have here is that I have here a picture of an ape, which classifies as a primate in ImageNet. And what I will do now is I will essentially find the, I will just follow the gradient to find the the closest image, such that it will make the model classify this image as a bird. Okay, so I will just morph this picture into the closest image that actually leads to classification as a bird. So let me do that. Done. So yeah, the model is not robust, so we should not be surprised. So there is actually, if you look very, very closely, there is a difference, but it's very tiny. The model is not robust, so clearly we can manipulate it the way we want it in a very, with a noise that is completely imperceptible. Okay? But let's try to do exactly the same experiment, but to a robust model. Okay? What will happen? Let's just do this. So this is what you get. So for your reference, this is not a bird. If you look very closely, you will realize that this is not a bird. Still, I think no one would blame the model for taking this image for being a bird. And again, all we did here is just train a standard model and just follow the gradient towards the over the loss to make the prediction be a bird. And we get such a very interesting and very semantically meaningful pictures. And of course, being where I am, I'm sure you clearly can draw the analogy to something you have seen. Because you have things like that. So there are generative adversarial networks that essentially is a very cool technology. But in particular, what it does, it allows you to come up with this very interesting latent embeddings, and then you can just navigate these latent embeddings, and kind of the pictures you get are something like that. So in some way, this is like really cool that we can get similar effects with robustness. In some way, it should not be surprising because in both cases, like when we do adversarial training, we are solving saddle point problem, and we are training guns, we are also solving saddle point problem. So you can view robustness as some kind of maybe restricted like gun like that produces like some restricted gun-like embedding. So there is still something to be understood here. But clearly we see that, okay, they had nothing to do with security, nothing to do with safety. Still, we got some desirable kind of, desirable property of the system just out of making it robust. Okay? So let me conclude. Let me actually wrap up. And yeah, so first of all, let's try to, so I hope, both Zico and I gave you like a little bit of a view of kind of where we are in adversarial robustness and kind of how to also get started. In particular, as Zico already said, the website has both the kind of more expanded version of what we talk about. It's still work in progress, but it will be there, and also has a code, so you can essentially start like playing with these things and see where they get. And as Zico said, this is very, very, very much open field. Like we really just scratch the surface. So just to give you some general direction that I think are kind of worth pursuing. So one frontier is algorithms. Essentially, one thing that is very like hampering us is just the inability to scale up all the technique. Okay, so essentially like having to do robust training, adversarial training, or doing verification is essentially like a real difficulty, and we really have to think about how, like what has to change to be able to play with larger models. Like MNIST is not really the right test case to do anything on this. Also, yeah, we have to think about like how can we make our models smaller and maybe more compact while still being robust, and actually, more importantly, how to change architecture to kind of maybe induce more robustness just in the prior. Okay, so maybe we should just rethink how exactly we even like put our networks together and kind of get some robustness just out of this. So that's one frontier. The other one is the theory. Okay, so in a sense, I think what I always find fascinating in a like standard ML was that the theory was actually very informative of what will happen in practice. Okay, so we had this kind of theoretical bounds, which of course were theoretical, but still usually the guidance they gave was quite crisp and quite relevant to happens in practice. Once the deep learning came in, we sort of lost it a little bit. We are slowly recovering it. And the same is true about robustness. Like I think at robustness, we still don't really have very good theoretical underpinning to even guide our intuition here. So in particular, we don't really have like strong or sufficiently meaningful non-vacuous like adversarial robustness generalization bounds. We know that adversarial generalization is different to standard generalization, but we kind of don't really understand it from the theoretical point of view. Also, as I said, maybe like we need some theory that will guide the choice of the regularization techniques, because the regularization techniques for robust classification that we have now, they do not seem to be effective. And finally, and this is actually, I can't stress this enough, there is this one more domain, is that this sort of the data. Okay, so machine learning is a field about data, and in order to make sure that our tools are really meaningful and they actually are broadly applicable, we really have to work with a diverse set of data sets. This is not really happening currently in the adversarial robustness world. Again, I'm guilty of this too, but kind of the reason is that we are so stuck at this moment that even we cannot figure out these very few data sets that we are working with currently, but that this should not stop us from trying to explore kind of how robustness manifests in many different scenarios. And also like the other extremely important point is essentially like, we have to think very hard about what are even the right set of perturbations that we should be considering. Like when I say my model should be robust, what is the exact kind of class of transformation that it will be robust to? As we said, the LP transformation that we consider, they are clearly necessary, but they are by far not sufficient, yes, because like rotations are not captured by LP perturbations, so you have to throw in rotations, then you can think of local deformation. Like there is a lot of stuff to think about, and I think we should think about. And again, this is just about vision, but there are many other contexts where this may be important and different perturbations have to be considered. So this is like kind of this three main goal: algorithm, theory, and data. This is where I would paint as the current the key directions that we should pursue in this field. But also, like, this is the point that already, Zico mentioned, but I really want to embrace is that somehow, there is something different about robust ML that goes beyond just like it works with different definition. Somehow this max in this definition should really, really make us also think differently about the way we approach the problems. Like, we should go from the kind of average and best case scenario evaluations to this kind of worst case mindset. Okay, so we really should think in particular, when we evaluate the quality of our model, we really should always kind of, think back. It's always a game. So yes, I want my model to succeed, but in order to make sure that I succeed, I have to put my hat of someone who wants to break it, someone who kind of knows exactly how it works, knows all the potential weak spots, and just tries hard to exploit it. So this is, again, something that happens naturally in security, because that's the field they work in. It didn't happen in machine learning, because there we didn't have to worry about adversarial yet. Now we have to, and now we really have to learn from security community, how to do it. I guess Nicolas Carlini is, one of the great, propagators of this kind of idea. So if you think your model is great, talk to him, and then you can talk after, right? So it's essentially he's great at that. There are some useful resources here. So there's a Clever Hans, which kind of gives you a library of attack. You should treat it as a point of start, not the end of your evaluation. This is just like, should just seed your thinking of how could I go about breaking the models. There's also a website, Robustml, that tries kind of to keep track of, like, as people propose models, which models actually were already, were proven to be robust, or at least there is some evidence that are robust, and which models were already circumvented. So you essentially can navigate the field better. But in general, like, it's really about the mindset. I think we really have to be much more skeptical and much more careful in this field that we usually are over there, because essentially failure here is kind of quite catastrophic, and we just can't afford that. Okay, so this is about adversarial robustness, but again, more broadly, I really want to kind of confirm that this is, like, in some ways, I think machine learning clearly succeeded as a proof of concept, but now it's time to go the next, to the next milestone. Essentially, like, make it truly reliable and kind of something that you can be kind of confident that you can deploy in the real world life, and essentially it will work there. And in particular, I really, really believe that thinking about robustness is not only will kind of bring us ML that is better suited for, like, security and safety aspect, I think it also will be better in other regards as well. I just mentioned this kind of interpretability angle. I think actually, like, in the context of fairness and other things, I think it also would be a very useful tool. Again, I don't know yet exactly how it will be useful. I think this is, like, the exciting question, but I am pretty sure that it will be. Okay, so this is all I have to say. I just want to, again, just emphasize, if you got interested in this field, there is, plenty of stuff to do. There is just, like, the kind of the cross-section of things to do is just overwhelming, to be honest. So yeah, if you want to get started, we have the notes and code over here, that you can just start playing with. We will be adding to it over and over. Also, like, some of these issues that we discovered, like, there are blog posts on my group website that kind of go a little bit in depth. They may also help you to get started. And yeah, overall, I just want to say, it's really fun field. I think it's really a critical field that we need an influx ideas and work. So I hope, some of you will decide to join in. I think it will be fun. Thanks.
Thank you so much. Hello. Can you hear me? Thank you. We have time for some questions. If you're leaving now, then please leave quietly. And if you have questions to ask, there is maybe just one microphone right here. If you could come and join the line. Go ahead, please.
So to summarize what you've done so far, if I'm the adversary, I put a max around the loss, and then you, the learner, put a min around the max to combat that. So let me ask the logical question, which is, what if I put a max around your min, and then you put another min around my max, and so on?
Sure. So yeah, I think it's like min and max, but yes, so I think what you are
more
getting...
more steps, more moves
yes.
in the game, if you will.
Well, again, in some ways, I think there is really just like one min and one max, because there is just like two players, adversary and us. But you are right that in some way this will always be a cat and mouse game. Essentially, like, whenever I kind of get an idea how to kind of thwart any of the attacks in one model, there's always a new kind of an extension of the model that kind of, oh, now we are not secure again. And yeah, in this way, we will never have ultimate robustness, but this is what we also have in the classical setting. It's like we never have perfect security. We just only try to reason about where we can get security at this moment, what we are missing, and kind of at least, you know, yeah, it will never be perfect, but we just need to do better than we do now. And hopefully in time, we will get there. But yes, there is no kind of, you know, solve it all solution that we just like, oh, now everything is secure, period, and there is nothing else to be done. That will be always an open question, but currently it's actually quite bad.
So one point I'll make there is I think the next regime for this, by the way, is the max over big delta. And that would be generalization over different classes of attacks, which I think is the next natural extension of this, which would be really interesting to consider, which really hasn't been considered very much.
And for example, being robust to multiple distance measures.
Yeah,
right?
Yeah.
So that you can do, take at the intersection or the union even, you can do that one. But to actually generalize and have an adversary that can adapt their perturbation region is a really open question that has not been addressed as far as I'm aware.
Yeah. Thanks.
Sir. Thank you for a great talk. It seems to me that in adversarial training, it is assumed that there is no intrinsic error in the computation of the training, but people have been trying hard to apply approximate computing, like reducing bit precision, so that when you compute, there will be some quantization error. Could you comment on how this robust machine learning would work with approximate computing?
Like, in the end, it's like, in some ways, these two things are orthogonal, because as Zico explained, in the end, when we want to get robust models, we just have to solve certain optimization problem. And yeah, so whatever we understand about solving these optimization problems in the reduced precision thing, it will transfer over. So I don't think it's an important issue, and we have to think about it, but I think we sort of have a very clear interface in which to understand what will be the impact of limited precision computation of this. It's just like, how well can we solve this optimization problem with limited precision? If we can do it well, everything will work. If we don't do it well, it will not work. So that's.
Okay, thank you.
Hi, so I think you talked about one approach being to find the exact worst case adversarial example, and you talked about using kind of off-the-shelf binary optimizers like Cplex, but I mean, I was wondering, like, the 0-1 binary programming problems are actually NP hard, and when you look at what optimizers like Cplex do, they're actually finding approximate solutions, like they're basically the branch and bound, they take like a linear relaxation, find an approximate solution, and then, you know, find another linear relaxation of the problem. So, you know, in terms of finding provably hard bounds, have you actually been able to do this successfully based on provably optimal solutions to the combinatorial problem, or?
Right, so the examples I gave there were for the networks, and the examples in the notebook. Those are all solving branch and bound to optimality. So you get the full, you expand the tree entirely to the point where you actually are guaranteed optimality, your upper and lower bounds match. Now, of course, you can also stop those solvers early in some sense to get upper and lower bounds which are do not meet. And actually, the convex relaxations I described there are exactly sort of like the first few relaxations that a method like Cplex or Groby would solve. And I should say there's also work, I think there's been some work from the University of Oxford and some folks at DeepMind on adapting like better branch and bound search methods for this problem. As I think it might even be a paper here at NeurIPS on that. So yes, there's a lot of work in this. There's also a lot of work on the SMT solver community about specialized solvers for these things that, again, compute upper and lower bounds. But to be clear, the solutions that we have in our tutorial are all the cases where you solve the branch and bound to completion where the upper and lower bounds match.
So, okay, all right. So, so how many dimensions have you been able to make this actually?
So for those ones that work exactly, there's about 80 hidden units in those, which is the number of binary variables.
Okay, all right. Thanks very much.
Thanks for the talk. What are your thoughts on ideas like input-free adversarial examples?
So what do meaning that you don't, what does input-free mean exactly?
Like you don't look at the input data when you're constructing your adversarial example.
I see. Oh yeah, so this is a very interesting question actually. Like in some ways, yeah, so not much, I think it's extremely interesting because in some ways you would like to kind of make your perturbations to be as kind of oblivious to where they will be applied as possible. So I don't think so. There is a work on universal perturbation, which is not exactly what you are talking about, but like it's close. It still looks at data, but you would like to come up with one perturbation that works for most of the images. So honestly, like input-free perturbations, I think, okay, so ideally, if we do well, unless there is some actual hidden bias in our machine learning models that we kind of is unwelcome, they will be kind of semantically meaningful. Like there should be just something that also should, confuse humans. So it will be very interesting to study if that is the case or not. So I think that's interesting, again, we are still starting. I think this is a very interesting topic. Yeah. I don't really know much about it.
Yes, so in the case of universal perturbations in particular, which are sort of getting at what you want, there's actually a very nice optimization formulation of that too, because you can just think about the max over delta being outside the sum now, or outside the expectation. So it's still a min-max problem, but the max is outside the expectation instead of inside of it. So it's independent of x. Or it has to be universal over all x. So that's sort of the universal perturbation formulation, which has been studied. What's been less studied, though, is models that are robust to universal perturbations, which should be an easier problem to handle. But there hasn't been much work on like robust optimization against universal perturbations. I think that's actually a really cool topic.
Thank you.
Hello, thank you for your excellent tutorial. The website is an especially nice touch. I was wondering, so you claim robustness at a particular bound, at a particular epsilon. But presumably if you were to increase the epsilon, you would then increase the error rate and so on and so forth. Has there been any research done, for example, on the detection of adversarial attacks, such that even if you were to increase the epsilon further and further, you still realize that your input is now adversarial and you should just like reject it or something, or do something sensible?
Yeah,
sure.
Why? Yeah, so we do have some work. It's sort of in progress, but I can talk about it. I'm not sure what we can do with it. Of just sort of simple like binary search on example-dependent epsilon boundaries that you can increase or decrease to sort of make each example as secure as it can be in some sense. I'm not sure it's quite getting what you want, but do you have more to say?
Generally, I think this is an interesting question. Like, I'm always a little bit skeptical of detecting adversarial examples because it's very unclear, like, if you make it data-driven, if you make it like machine learning algorithm that is supposed to detect stuff, then what you can do, you can construct adversarial examples against this detector. So this is like the most promising way to do it. It's definitely not, I don't think it works. Doesn't mean it cannot be done, but yeah, I think the interesting meta question over here is exactly like how much our methods overfit to the choice of epsilon. Okay, so we definitely did this kind of studies where we kind of took a model that that is like designed to be robust to 0.1 epsilon, and like how does it fare when you go beyond it? And of course it gets broken. It's depending on the data set. It's really like it clearly overfits, and sometimes it just like relatively gracefully goes back. And sometimes you actually want to kind of attack it in a stronger manner to just get a security against smaller epsilon. So there, I think we don't understand it well. There's clearly something interesting happening, but yeah, we don't know it.
Okay, thank you.
Hi, thanks again for the talk. It was excellent.
So only one or two more questions. So
okay. My question is actually about the nature of the threat models, the attackers, and the inputs they'll choose, and that I think in most threat models you're going to find the attacker is free to choose inputs to perturb that are outside the distribution of the task at hand. You gave a really good example of Carlini's work where he used music to attack speech to text. Yeah. And I think most of the threat models I've looked at, this is perfectly available to the attacker, and I'm curious if you see any path forward for adversarial training and verification when you have to actually deal with the whole family of distributions that lie outside your task.
Yeah.
Yes, so I can definitely see it. I don't know how to do it.
Yes, I don't either.
Yeah, I agree.
Yeah,
it's an actual problem if you say so what prevents noise from being classified as something well? Because it could be any noise anywhere, right? That's a great
adversarial graffiti.
We don't know yet.
Right.
Yeah, so I expect that this will be like a big problem. Like I have some thoughts how to go. Like I think essentially part of the problem might be that we are asking for too much. I think we should not be able to robustly classify noise as well. But yeah, currently, if you start with complete noise, you will destroy this model. There is no question about that.
Okay, yeah. To your point about asking too much, I think this is where the engagement with the security community, which is where I actually come from, has to really start in earnest.
Exactly.
Because it will be the threat models, not the ML, that define what's too much, so to speak.
Yeah, I'm happy to chat. That's exactly what I think.
Excellent. Thank you.
Yeah.
Thanks for giving
Make it a quick one, please. Okay, so most of the tutorial are about image object detection, and I just wonder if there's any results on natural language processing, like question answer in those areas.
Yeah.
Thank you.
So yes, there is. I know Percy Liang and Daniel Loud have some, each independently have some work on that. Nicholas Carlini, right, sitting by you, has some work on speech, as was mentioned in the previous one. So yes. Language is different in particular because it's much more discrete than images. So you change a whole word, you don't just perturb a word a little bit. But there is work on that. It's not as well developed, but there definitely is some work on that.
Yes.
So like at the latest EMNLP, there were several papers on this.
Yes, so in a sense, problem with NLP is that like we still are not there yet with average case performance. So in some ways, it obviously doesn't work when you do adversarial stuff, but yeah, there is work again. Percy Liang, I think, is one of the lead persons on that. So yeah, but yeah, it should apply to any domain. It's just a matter of time.
All right.
Thank you.
It's the end of the tutorial. Let's thank Zico and Alex again. Thank you very much for a great tutorial.